Hello, and welcome to this presentation that has been designed for students studying virtual engineering, a unit that involves modeling various design configurations using Finite Element Analysis, FEA. This presentation presents various scenarios, predominantly of beam bending analysis, that can be modeled using virtual engineering techniques. It is preferable if you have seen the previous presentations related to beam bending analysis and are familiar with bending stresses and also direct or axial stresses that can be induced in members due to applied loading. However, the presentation has been written in a way that if you have not been exposed to calculating bending stresses using engineer's bending theory, that the coverage here should be sufficient to give you a reasonable understanding of how to analyse the various problems that the presentation poses to students. Here's a presentation overview. We commence with a brief introduction that contains extracts from previous presentations, and these include a review of simple engineer's bending theory, types of loading applied to beams, types of beam, including formulae for calculating the maximum bending moment, and also deflections of various types of beams. Predominantly our types of beams will be cantilever beams and simply supported beams. Formulae for section properties related to standard sections are listed, and also material mechanical properties of some common materials are stated. Then we have the commencement of the examples. Example 1 relates to a cantilever beam, as shown in this illustration here. We're going to calculate the maximum bending stresses in the beam and the maximum deflection of the beam. Example 2 relates to a simply supported beam, shown here. Again, we'll calculate the maximum bending stress in the beam. And example 3 as another cantilever beam, but this time with axial and bending loading applied. This is example 3 here. So this is our axial compressive loading applied, shown P, and we also have bending of the cantilever beam applied in two directions here. And again, the essence is here is that the examples shown we can analyse using techniques we've covered in previous presentations, but then we can model them on our various finite element packages and review the correlation between the theoretical results and the computer-based results. There are exercises related to each of the examples for you to undertake by hand to help you understand the process of analysis here. And finally, the presentation does conclude with a brief summary of the various examples and associated exercises, and also provides an overview as to the development of the finite element model. In other words, considering some of the salient requirements when developing the FEM, and also considering the output from the FEM. And for reference, here are approximate start times related to the commencement of the various sections contained within the presentation, hopefully to aid your ease of access through the presentation. But please note, these are only approximate start times. Let's review simple bending. Consider a beam made of an elastic material subjected to an applied bending moment, symbol capital M, as shown in figure 1 here. So here's our beam. It's subjected to an applied bending moment. The bending moment will induce a radius of curvature, symbol R here. And the bending moment induces maximum tension in the lower face of the beam, as shown here, and maximum compression in the upper face of the beam, shown here. As we've seen in previous presentations related to simple bending, the stress distribution across the beam, shown here, is of a triangular distribution. We have zero stress at what's termed the neutral axis of the beam, centre of the beam in this case, and then the stress varies linearly from the neutral axis to the maximum stress, in this case At the bottom of the beam, maximum stress is in tension, and the top of the beam in this particular scenario, the maximum stress is compressive. The distance shown as y here, the centre line of our section to the outside surface. The neutral axis is the location where there is no strain in the member, so there's no bending stress occurring at the neutral axis. So such a beam configuration as that shown on the previous slide can be analysed in simple bending by using what's known as engineer's bending theory, EBT for short. So engineer's bending theory is shown in the bolded box here and stated without proof in this presentation. So let's consider the variables. So capital M is the applied bending moment. Unit can be Newton meters, but we'll predominantly use Newton millimeters in this presentation. Symbol I is termed the second moment of area. In some older textbooks, is sometimes referred to as the moment of inertia, but that's slightly misnamed. But we'll refer to the second moment of area in this presentation. And that's considered about what's termed the neutral axis. The unit of I is meters to the 4, but we'll be using millimeters to the 4 within this presentation. Just note for reference that the second moment of area relates to the beam's bending stiffness. Lowercase sigma is the bending stress in newtons per millimeter squared. Symbol Y is the distance from the neutral axis, the zero strain position within our beam, to the fibre under stress, the fibre we're considering, and Y will be stated in millimeters in the calculations we're undertaking here. And for the standard sections we'll be reviewing, Y is always half of the section depth. Symbol capital E is the modulus of elasticity, also termed Young's modulus, newtons per millimeter squared. And finally capital R, we mentioned previously, is the radius of curvature of the neutral axis, and that'll be in millimeters. There is another property often used when we're analysing bending in beams, and that's termed the elastic section modulus, symbol Z. Note the Z value relates to the beam's bending strength. Z is calculated from the second area moment value divided by the maximum Y value, the maximum distance from the neutral axis to the extreme fibre of the beam, outside of the beam in our case. And we can use the section modulus value to calculate the bending stress as shown in the bolded box here. The maximum bending stress is equal to the applied bending moment divided by what's termed the minimum section modulus, Z min shown here. That's the second area moment I divided by the Y max. Also within this work we will consider the factor of safety, FOS for short, and for this presentation the factor of safety is defined as follows. FOS is equal to the material's yield strength, denoted sigma y, divided by the working stress, the induced stress in our member, symbol sigma. Let's consider types of loading to our beam. For our previous presentations on beam bending, we considered two types of applied loading. The first is concentrated point loads. These act at one specific point on the beam. They applied at effectively a knife edge on the beam. And also we'll consider uniformly distributed loadings, UDL. These can act over all or a portion of the beam. Note that UDLs are generally specified in terms of newtons per meter or newtons per millimeter. And of course in practice beams may be subjected to combinations of point loads and UDLs. Let's consider the types of beam. So beams can be supported in various ways. But within this presentation we're just going to consider simply supported beams at both ends. So left hand diagram here we'd have a reaction here and a reaction here. This illustration with a point load in the middle. So this is our simply supported beam here. And also we'll consider built-in at one end only beams. They're referred to as cantilever beams. So considering the diving board scenario here, the cantilever beam is effectively built in at this end here. Sometimes we call this the wall location because often it can be a wall in practice. And for cantilever beams there'll be a vertical reaction here at the wall and also a fixing moment at the wall. So that's a cantilever beam. Here's an extract from table 1 of our notes showing the beam configurations and the types of loading. On the left hand side again we have our simply supported beams. In this case applied load in the middle from the person standing in the middle of the beam, and this is reacted at the ends of the beam. And if we want to calculate the maximum bending moment which would occur in the middle of the beam, the maximum bending moment is given here is PL divided by 4. P is the applied load and L is the length of the beam. For our cantilever beam scenario, as I said before, we have the vertical reaction at the wall here, RW, and of course the fixing moment at the wall here, labelled MW. To calculate the maximum bending moment for a cantilever beam, that occurs at the wall, and the maximum bending moment is given as P multiplied by L. Again, P is the applied load and L is the length of the beam. Here's our table 1, beam configurations, types of loading continued. On the left hand side we now have a UDL along the entire length of the beam. The UDL is denoted as shown here and often given the symbol omega. So again a simply supported beam reaction at either end here with a UDL applied. The maximum bending moment again occurs at the midspan for the simply supported beam, and I've stated the maximum bending moment in two forms here. As within textbooks, the maximum bending moment can be expressed in either form. So the first form for maximum bending moment is omega L squared divided by 8, or the maximum bending moment can be expressed as W L divided by 8, where the W is actually omega L. So use whichever equation relates to the information given in the question. Similarly, for the cantilever beam, again in this scenario we have a uniformly distributed load along the entire length of the beam, again denoted as omega, our vertical reaction here and our maximum moment of the wall. And again the maximum bending moment is stated in two forms. The bending moment of the wall can be stated as omega L squared divided by 2, or the maximum bending moment at the wall can be stated as W L divided by 2. Let's consider standard beam cases related to deflections. So deflection formulae can be determined by various techniques such as strain energy, Macaulay's method, which both involve use of the calculus, in other words using integration. However, in this presentation only a general treatment is considered, and thus deflection formulae for a few common cases of beam loadings will be stated without proof in our table 2 shown on the next slide. So here's table 2, relates to beam maximum bending moments and deflections. Bending moments are repeated just for reference here. So firstly, for a simply supported beam with a point load at the midspan of the beam, P shown here, centre of the beam, we know from the previous slide the maximum bending moment at the midspan. If we now want to calculate the maximum deflection, symbol delta here, the maximum deflection occurs at the midspan, and it's given without proof here as PL cubed divided by 48 EI. P is the applied load, of course, L is the length of the beam, E is the Young's modulus, and I is the second moment of area. We outlined these terms previously. And if we consider a simply supported beam with now a UDL over the entire length of the beam, again on the left hand side here we repeated the maximum bending moment at the midspan. The maximum deflection occurring at the midspan is given now as 5PL cubed divided by 384 multiplied by E multiplied by I. Just be careful in the problems we're going to review as to the type of loading and choose the appropriate formula for the analysis being undertaken. Table 2 continued. Now we're considering cantilever beams initially with a point load applied at the free end. Here, again, the maximum bend moment occurs at the wall this time, position A. And if we want the maximum deflection at the free end, the delta max, for a cantilever beam, that's stated as PL cubed upon 3EI. And considering a cantilever beam now with a UDL over the entire span, again, maximum bending moment shown here at the wall, but the maximum deflection at the free end is now PL cubed upon 8EI. So these deflection equations are given without proof, but as I said previously, they can be proved from various techniques such as Macaulay's method, strain energy, etc. Let's consider section properties. So in table 3 here, we've got section properties of common shapes, quite simple shapes we're going to use in this presentation. For each section type, we have the area formula stated in this column. We have the second moment of area, symbol I, formula stated in this column. And we have the section modulus in this column. This is actually minimum section moduli values we are calculating within this column. So the first row, formulae related to a square section. Notice within each section we have an x and y axis referenced. It doesn't matter for the square section, of course, the x and the y I values will be the same for the square as will the z x and the z y values. But for the rectangular section, the ix and the iy values will be different formulae here. Of course, the zx and the zy values will be different also. Table 3, section properties of common shapes continued here. Here we have properties for the circle and also for the annulus. I'll let you review this slide at your own pace. So essentially, table 3 of our notes have standard section properties that we'll be referring to when we undertake our analysis later in the presentation. And purely for reference, table 4 states typical mechanical properties at ambient temperature, room temperature, of various material properties that are often used within engineering. This table is purely for illustrative purposes to make you aware of the type of material properties required to be input to an FEA package. So for aluminium alloy, for example, we have the Young's modulus stated here, the E, 70 kilonewtons per millimeter squared. And we also have other parameters stated that we will not necessarily use within this presentation, but when you model, you use finite element analysis, you often have to state these values because although most of our problems here are two-dimensional, obviously in an FEA environment, we often consider three-dimensional problems. So Poisson's ratio, Greek symbol nu, rigidity modulus, symbol capital G, and also mass density, symbol rho, will be required as inputs to the finite element analysis. And you'll probably find that there's an inbuilt database within the FEA package, although the specific values of Young's modulus, etc., may be slightly different in the standard properties in the package. And just note for reference that 70 kilonewtons per millimeter squared could be stated as 70 giganewtons per meter squared or 70 gigapascals. And here are some other common materials stated in the table, again purely for reference. We'll refer to some of these properties within the calculations we're going to undertake. Let's consider our first example. Example 1 relates to a cantilever beam. So the cantilever beam shown in the sketch on the right hand side here is used to support a bogie attached to a hoist that can move along the lower flange of the cantilever beam. The joist section that's used in the design has a serial size of 102 by 102 by 23.07 kilograms per meter. The various properties for this section are shown in table 5, which will show on the next slide. The length L is 3 meters, this length here, and the maximum weight, symbol P, that can be carried by the beam is 1.5 kilonewtons. So this is the weight that's applied. We will consider the weight to be located at the free end of the beam for analysis purposes. So that's up at this end of the beam here, because that presents the worst loading scenario to the beam. But in this analysis, we're ignoring any flange bending that could occur. We're just considering the overall I section in bending. So, part A, extracting the appropriate section modulus value from table 5, we've got to determine the bending stress, sigma, at the wall. That's the maximum bending stress in the beam. In part B, if the yield strength, sigma y, of the material used is 275 newtons per millimeter squared, we've got to calculate the factor of safety. And part C, extracting the second moment of area from table 5 on the next slide, and assuming the Young's modulus is 205 kilonewtons per millimeter squared, we've got to find the maximum deflection of the beam. So that's example 1 outlined. Let's now consider the solution for example 1. So here's table 5. It relates to an extract of BS4 part 1 1980 related to joists. In the question, we're asked to consider a serial size of 102 by 102 millimeters and a mass per meter of 23.07. That's kilograms per meter. If we now look in the table 5 for the section properties, so table 5, continued. Here's again the serial size and the mass per meter we're using. We need to now extract the section modulus for our particular section. Notice we're bending about the x-axis of the beam. We always try and design our beams so that where possible we bend about the stiffest axis. On our table here, this is the XX column. And for our particular section, we read a value of 95.72, note the unit centimetre cubed. We will also require the second moment of area, again about the XX axis. And from our table, reading the 102 by 102 serial size row, then the I value, the second moment of area, is 486.1, note the unit centimetres to the 4. So those are the section properties we'll require for this particular joist within our calculations. So we need to make a note of them. So on this slide here, I've actually stated some unity brackets. We've used unity brackets in previous presentations to help structure conversions from one unit to another unit. And I've just shown you on this slide the linear conversion from centimeters to millimeters. It's a factor of 10 between the centimeter value and the millimeter value. If we're converting areas, then we'll find that there's a factor of 100 in our conversions. If we're converting our section moduli, Z values, from centimeters cubed to millimeters cubed, there'll be a factor of 1000. And if we're converting our second moment of area, I values, from centimeters to the 4 to millimeters to the 4, there's a factor of 10,000. And we derive those factors through the use of unity brackets. Unity brackets continued. I've also shown here, for reference, conversions of stresses, sigma, from meganewtons per meter squared to newtons per millimeter squared, and also the reverse conversion, and a similar conversion for elastic moduli, again from giganewtons per meter squared here into kilonewtons per millimeter squared, and vice versa. So again, just showing you the unity brackets should you need to undertake any conversions within the exercises. There's a separate presentation related to the use of unity brackets. And again, purely for reference, I've listed the various prefixes. The commonly used prefixes in mechanical engineering are giga, mega and kilo, and milli and micro. Just showing the various power notations here for reference. So back to our example 1. Here's the solution now. So extracting the information from the question, the beam's length L is 3 meters. I'll convert that immediately into millimeters because I'm going to use millimeters in my calculation. So that's 3,000 millimeters. The force P at the free end of the beam, 1500 newtons. That's the 1.5 kilonewtons stated in the question. And we know from the previous slide, the section modulus from table 5 is 95.72 centimeters cubed. We need to multiply that by 1,000 or 10 cubed from our unity bracket conversion. So the ZX value is 95,720 millimeters cubed. And also from table 5, the second moment of area about the x-axis was 486.1 centimeters to the 4, and we know we have to multiply that by 10,000 or 10 to the 4 to convert to millimeters to the 4. So that's 48.61 times 10 to the 6 millimeters to the 4. So there are our section properties extracted from our standard in table 5, converted into the appropriate unit for the calculations. So example 1, solution continued. So part A, we're asked to calculate the bending stress at the wall, which is of course the maximum bending stress in this case. So firstly here I've calculated the maximum bending moment in the beam at the wall. From our previous tables, the maximum bending moment in the cantilever beam is P multiplied by L. So in this case that's the 1500 newtons multiplied by 3000 millimeters. So 4.5 times 10 to the 6 Newton millimeters is the maximum bending moment. And then step 2 here, I've calculated the maximum bending stress, sigma. So sigma is simply the maximum bending moment divided by the minimum section modulus from the previous slide. So that evaluates to a bending stress of 47 newtons per millimeter squared. Example 1, solution continued. So part B, we have to calculate the factor of safety, given that the yield strength sigma y is 275 newtons per millimeter squared. So factor of safety is the yield strength, 275, divided by the working stress, the induced stress of 47 newtons per millimeter squared, calculated on the previous slide. So the factor of safety is 5.85. So 5.85 times stronger than required in this particular case, which might be quite reasonable in practice, as this beam is obviously used for lifting purposes, so you might want a significant factor of safety on the beam. The materials would be expected to be quite cheap in this case, so probably no significant cost for having a larger beam. Part C, we're asked to calculate the free end, that's the maximum deflection, again using the appropriate table on our previous slides. So deflection delta from the formula is WL cubed divided by 3EI. In the question, the Young's modulus, that's the E value, is 205 kilonewtons per millimeter squared. So we'll insert that value into the equation to use. We have the W or the P value, in this case, that's 1500. We have the length of the beam, L, 3000, so that's 3000 cubed. And we have the I value from our table on the previous slide. So the deflection at the free end here calculates to be 1.35 millimeters. I'll leave you with exercise 1. Exercise 1 is basically a repeat of example 1, but with different numerical values. This time the load P is 2000 newtons, the length of the cantilever beam is 4.5 meters, and the joist size from our table is now a 152 by 127 by 37.2 kilograms per meter. Answers are shown in the bracket for the maximum stress, for the factor of safety, and for the free end deflection. Exercise 1 continued here. Here's an extract from the table 5, BS4 part 1 for Joyce. And here is the serial size we're considering. So here is the section modulus about the XX axis. We'll need to extract for this section. It's 238.7 centimeters cubed. And here is the second moment of area value, again about the XX axis. And that's 1,818 centimeters to the 4. So those are the properties you'll require within the calculation for exercise 1. I encourage you to start the presentation and attempt exercise 1. As I said, very similar to example 1, just the different numerical values to work through. Let's consider now example 2 relating to a simply supported beam. So a simply supported timber beam has a span length of 2 meters, that's L here. It carries a central point load labelled as P of 800 newtons. If the beam has a rectangular cross section of 72 millimeters wide, 97 millimeters deep, we're asked to calculate A, the maximum bending moment that occurs at the center of the beam, and then the associated maximum bending stress at this location here. Part B, the factor of safety, if the maximum allowable stress for the timber is limited to 14 newtons per millimeter squared. In part C, we've got to determine if the beam's deflection is acceptable, assuming that the allowable deflection for the beam must be no greater than the span length L divided by 200, assuming the Young's modulus, the E value, is 2.7 kilonewtons per millimeter squared. So that's example 2 outlined. Let's now consider the solution for example 2. So example 2, here's the beginning of the solution. As always, we firstly extract the information from the question. So the applied load P given in the question is 800 newtons. The beam span length L is actually stated as 2 meters. I'll convert that to millimeters here, so 2000 millimeters. And the width denoted as B in my diagram here is 72 millimeters, and the depth D is 97 millimeters. We were also given the maximum allowable stress is 14 newtons per millimeter squared, and the Young's modulus E is 2,700 newtons per millimeter squared. Those values were stated in the question. So the first thing I'm going to do is to calculate the beam section properties using the various formulae from table 3 on our previous slide. So first of all, let's calculate the section modulus. That will be about the XX axis here. The section modulus is BD squared divided by 6. Here's our Z about the x-axis, BD squared upon 6 from table 3 here. So inserting the values, the B is 72, the D is 97, which we square, divide that by 6. So 112.9 times 10 to the 3 millimeters cubed is our Z value about the XX axis. So stiffest section for the timber beam here. And to calculate the second moment of area I, the formula from our table is BD cubed upon 12. Here's our formula I BD cubed upon 12, our previous slide. Again inserting the values for B and D and evaluating, the I is 5.476 times 10 to the 6 millimeters to the 4. So there's our section properties that we'll need to calculate the bending stress and also the deflection of the beam. Example 2, the solution continued here. Let's now determine part A. That's the maximum bending stress occurs at the midspan of the beam here under the load. So step 1 here, we're going to calculate the maximum bending moment, M. From our table 2 on our previous slide, the maximum moment at the center of the beam is PL divided by 4. Here's the formula from the previous slide for ease of reference. P in this case is 800 newtons. The length of the beam is 2 meters or 2000 millimeters. So evaluating the maximum bending moment is 400 times 10 to the 3 Newton millimeters. And then step 2 here to calculate the maximum bending stress. Formula here is stress is equal to the maximum bending moment divided by our section modulus from the previous slide. Inserting the M from above and the Z from the previous slide. That evaluates to a maximum bending stress in our timber beam of 3.54 newtons per millimeter squared. Example 2, solution continued. So part B, we're asked to determine the factor of safety, which is the maximum allowable stress in this case. Sigma Y labelled here, 14 newtons per millimeter squared, divided by the working stress calculated on the previous slide. So the factor of safety evaluates to 3.95, approximately 4. Part C now, we've got to determine the maximum deflection, occurs at the midspan. So again, from our previous table, we can extract the appropriate formula for the deflection of a simply supported beam at the midspan. And for ease of reference, here's the formula from our previous table for the central deflection of a simply supported beam. Firstly, though, I've calculated the allowable deflection, which we were told in the question is the span length divided by 200. So L divided by 200. That's 2000 millimeters divided by 200. So the maximum deflection we're permitted from our standard is 10 millimeters. If we now use the appropriate formula from our table for the midspan deflection of a simply supported beam, it's PL cubed divided by 48 EI. In the question above, we know the P is 800 newtons. The length of the beam is 2000 millimeters, so 2000 cubed. That's all divided by the 48 multiplied by the E value, giving us 2.7 kilonewtons per millimeter squared. So that's 2700 newtons per millimeter squared here. And the I value calculated on the previous slide, 5.476 times 10 to the 6 millimeters to the 4. This value here. So that evaluates to a maximum deflection of 9 millimeters. So that would be acceptable in this case because the allowable deflection, given the limit stated in the question, is 10 millimeters. Here's exercise 2. It's basically a repeat of the calculation in example 2, but this time p-value is 1.6 kilonewtons. All other parameters stay the same. We're asking exercise 2 to compare and contrast the answers for the stress, the factor of safety and the deflection, and then just to comment on what's noted. Here are the answers of part A, so maximum stress in the beam, part B, the factor of safety, and part C, the deflection of the beam. I'll let you undertake exercise 2 and draw the appropriate conclusions. Let's consider now example 3. This is a cantilever beam again, but with multi-dimensional loading. In other words, you'll see we've got 3 multi-orthogonal loads applied to the free end of the cantilever beam. So the cantilever beam shown in the sketch is used as part of a supporting structure of a building. The beam has a length L of 3.5 meters and is made from a rectangular hollow section, RHS section, having the dimensions 150 by 100 and a wall thickness of 12.5 millimeters. The section properties for the RHS section are shown in table 6 on a later slide here. This cantilever beam has to withstand a load W of 200 kilograms. Be careful of the unit there for W, as well as a concurrently applied compressive axial force, labelled as P in the diagram, of 100 kilonewtons, and also a lateral force, labelled F in the diagram, of 900 newtons. For the cantilever beam in example 3, we've got to calculate A, the maximum tension and compression stresses that occur in the beam at the wall location up here. Part B, if the beam's material yield strength is 245 megapascals, we've got to calculate the minimum factor of safety. In part C, we've got to calculate the resultant deflection due to the bending forces applied. So there's example 3 outlined. Let's now consider the solution for this problem. Firstly, a brief recap here for calculating direct or axial stresses, symbol sigma. From our previous presentation related to direct stresses, the stress, sigma, in an axially loaded member, force P applied at the ends of the member, so the tension member in this case. So the formula for stress is simply the applied force P divided by the cross-sectional area of our particular section, A. And the unit for stress would be the Newton per meter squared or Newton per millimeter squared. I've just extracted an example from our previous lecture on direct stresses to show how the direct stress is actually calculated. In an example given, the force applied over the cross-sectional area is calculated here. So simply P divided by A to work out the direct, or in this case the tensile stress in the member. Notice I've used newtons per meter squared here for my unit. That's just a recap because we're going to consider a compressive direct stress in this example 3 we're currently considering. Also, here's an extract from table 6 of our notes related to a British standard associated with hot finish rectangles, RHS sections, and we're also given the Young's modulus for this particular steel again. Note the nomenclature used, the B is the width and H in this case is the height. Often we use D for height within our calculations. And capital T here is the wall thickness of the RHS section. In example 3, we're asked to use the section denoted here of 150 by 100 by 12.5 millimeters wall thickness. So we need to extract the appropriate information here for the section. But notice in this question we'll be bending about the XX and the YY axis. So we will need the section modulus about the XX and the YY axis. So symbol W has been used in this particular table for the Z values about the XX and the YY axis. So reading from the table, the Z about the XX axis is 198 centimeters cubed, and the Z about the YY axis is 153 centimeters cubed. Considering the second moment of area, here's our IXX and our IYY. Reading the IXX, it's 1,488 centimeters to the 4. And reading the IYY, it's 763 centimeters to the 4. We also need the cross-sectional area in this case, A, which is 54.6 centimeters squared. So those are the section properties required, extracted from the appropriate standard, in which we need to make a note of because we will use them in our following calculations. So example 3, continued. Let's consider first of all part A. We're going to determine the maximum tension and compression stresses that occur at the wall. I said there's a slightly more complicated problem here because we have three-dimensional loading applied to the beam. So example 3, here's the solution. Extracting information from the question, the length was 3,500 millimeters. The actual compressive load P was 100 times 10 to the 3 newtons. The weight force W, be careful here, the W value was actually stated as a mass of 200 kilograms. So we multiply that by 9.81 to calculate the weight force. So the actual force W is 1,962 newtons. And the lateral force F, shown here, was 900 newtons. So that's the information extracted from the question. Below are the section properties from our previous table related to the section we're using. So from our table 6, here's a recap of the properties here. The area, 54.6 centimeters squared. Multiply that by 100 to convert it into millimeters squared. Here's our section moduli. Zx was 198 centimeters cubed. Multiply that by 1,000 to convert it to millimeters cubed. The Zy, 153 centimeters cubed. Convert that into millimeters cubed. And the second motive area value about the x-axis, Ix, was 1,488 centimeters to the 4. We multiply that by 10 to the 4 or 10,000 to convert to millimeters to the 4. And similar approach for the I about the y-axis, 763 centimeters to the 4 converted to millimeters to the 4. So there's our section properties converted into the appropriate units for the calculation. So example 3, solution continued. This is now part A. We have to calculate the maximum stresses at the wall. Now, the maximum tensile stress at the wall will occur at this location here, and the maximum compressive stress will occur at this location at the wall. If you think of the applied bending, so force F here would produce tension at this point here, but compression at this point here. Force W would produce tension at this point here and compression at this point here. And the actual force P produces compression at this point here and of course compression at this point here. So calculating the compressive stress, sigma C, I've labelled it here, we have the negative P upon A stress from the direct compression. We have the compressive stress due to the W times L, bending moment applied. It's about the ZX axis, this axis of our section. Then we have the compressive stress due to the bending moment F multiplied by L, and that's about the y-axis, so divided by the ZY. This is the YY axis. Inserting the values to calculate the actual compressive stress, the compressive stress due to bending about the x-axis, and the compressive stress due to bending about the y-axis. So evaluating the maximum compressive stress at this location here is 73.6 newtons per millimeter squared. The negative means compression. Just note for reference, we're actually using the concept of superposition here when we work out the combined effect of the three load cases. We're effectively superimposing each case on top of each other and adding up the cumulative effect to find the net effect. But note that superposition can only be applied as long as the stresses remain within the elastic region of the material, and also that the deflections produced are considered to be small. If we now calculate the maximum net tension stress, sigma T here, we still have the net compressive stress, negative 18.3, But this time the bending stress about the x-axis is actually positive, and so is the bending stress about the y-axis positive. So the maximum net tension stress, sigma T, at this point here, evaluates to be 37 newtons per millimeter squared. I would encourage you to stop the presentation and think carefully through the calculations on this slide and try and understand how the positive and negative bending stresses are induced at the wall from the various forces applied. It can be quite a conceptually difficult calculation here to understand. Example 3, solution continued. So part B, we have to determine the factor of safety. We're given in the question the yield strength of the material is 245 meganewtons per meter squared. That's the same as 245 newtons per millimeter squared if you use the appropriate unity bracket. And we divide the yield strengths by the maximum net stress we calculated on the previous slide, which was actually a compressive stress of 73.6 newtons per millimeter squared. So evaluating the factor of safety is 3.3, nominally speaking. And then part C, we're asked to calculate the free end maximum deflection. So again, referring to table 2 on our previous slide, we can find the deflection formula relevant here. We will again assume the allowable deflection at the end of the cantilever beam to be the span length, which is 3,500 millimeters in this case, divided by 200. So the maximum allowable deflection would be 17.5 millimeters. So evaluating the deflection due to load W, the formula from our previous slide would be WL cubed upon 3EI. Again, note the deflection due to W is about the XX axis here. So inserting our values for W, for L, for E, and for I about the XX axis, that's 9.2 millimeters. We now consider deflection due to force F, the lateral force here. That's now a deflection about the YY axis, the less stiff axis here. Again, using the same formula, we just put the value of F in this time and the value of IY. So that's the only differences here to the equation. That evaluates to a lateral deflection of 8.22 millimeters. To find the resultant deflection delta, we simply use Pythagoras theorem, and it's delta W squared added to delta F squared, all square rooted. Inserting the values, the resultant deflection is 12.3 millimeters. So if the allowable deflection is 17.5 millimeters, then the 12.3 millimeters is acceptable. So there's the full worked solution for example 3. More complicated question in the fact that we're bending in 2 directions, and we also have the applied compressive force from load P acting on our beam. Example 3, solution continued. On this slide, I've just tried to illustrate in greater clarity the various deflections that have been calculated on the previous slide. And just note for reference, the term displacement is also used in this context to describe movement of one point relative to a datum point. And of course, in the case of this cantilever beam, our deflections or displacements at the free end are relative to fixed point at the wall. I'm using the terms deflection and displacement interchangeably here. So firstly, we considered force W applied at the free end of the beam, and so we could calculate the associated deflection, delta W. Then we considered the lateral force F applied at the end of the beam. Force F induces this deflection shown here, labelled delta F. And using Pythagoras' theorem, we can calculate the resultant deflection because we now know delta W, we know delta F. We can calculate the resultant deflection or the resultant displacement labelled delta here. And the resultant deflection is indicated by this vector here, at the end of our beam. Just note for reference, there would be a deflection due to applied compressive force P at the end of the beam. As this is an actual compressive force, then the beam would obviously shorten, but we're making the assumption that the deflection due to the applied axial force P is negligible compared to the deflections due to bending. I'll leave you with exercise 3, which is essentially a repeat calculation of example 3, but this time we're going to use a different RHS section. It's a 120 by 80 by 10 millimeters section. Again, table 6 of our slide will show the properties for that. Reference again, here's the extract from table 6 of our notes, the British standard related to rectangular hollow sections. And for a 120 by 80 by 10 section, shown here in our table, we again can read off the appropriate properties. The area is 34.9 centimeters squared. The second moment of area about the x-axis is 609 centimeters to the 4, and about the y-axis it's 313 centimeters to the 4. And finally, the section modulus, the z values, about the x-axis, 102 centimeters cubed, and about the y-axis, 78.1 centimeters cubed. So we'll need to use those values in the calculations. So in exercise 3, we're asked to comment on the factor of safety found and the resultant deflection calculated. Given a beam length L is 4,200 millimeters, the actual compression P 80 times 10 to the 3 newtons, the load W 150 kilograms, again be careful with that piece of information, and the lateral force F is 450 newtons. Answers shown in the bracket here for part A, the maximum stress, again compressive stress here, part B for the factor of safety, and part C, the deflection. Again, the allowable deflection would be assumed to be the span or beam length L divided by 200. I would encourage you to start the presentation and solve exercise 3 following the same procedure used in example 3. Here again are the properties for the 120 by 80 by 10 RHS section. I just stated these section properties again on this slide for further clarity. So here's a summary of the 3 examples we considered. Example 1 was the cantilever beam with the applied force at the free end of the beam. Example 2 was the simply supported beam with the applied point load at the midspan. And example 3 was another cantilever beam, but this time with multi-dimensional loading at the free end of the beam. Hopefully you've attempted the exercises associated with the 3 examples, and for reference, exercise 2, which was based on example 2, to comment on what was noted about the results of exercise 2 compared to example 2. The only difference between example 2 and exercise 2 was the applied load, and as we are considering a linear static analysis here, you should have found that the stress, the factor of safety and the deflection are proportional to the applied load. So as the load on the beam was doubled, that meant the stress was doubled, the factor of safety would be halved, and the deflection would have been doubled, which would make it now unacceptable compared to the allowable deflection of span lengths divided by 200. So now you're in a position where you can begin to develop your Finite Element Model, FEM for short. You have now an array of problems that have been analysed using hand analysis, and you can now generate the appropriate models and compare and contrast the solutions between the finite element analysis and the classical analysis from the hand calcs. So for reference, we're now constructing the finite element model. There are various considerations to now review. So you need to consider the type of analysis, in this case I would suggest that's linear static analysis. You then need to input the geometry of the respective beam configuration, input the various section properties for the beam, the various material properties, consider the applied loading, and also the restraints in both translation, that's X, Y, and Z axes, and also in rotation about the X, Y, and Z axes. Note that example 1 and 2 are essentially two-dimensional problems, but the FEA analysis will be a three-dimensional environment, so you will need to apply appropriate fixations, even though analysing a two-dimensional problem. And example 3, of course, is three-dimensional because it has three-dimensional loading applied. You would then need to consider the results, and I would suggest you need to output the reactions for the beam configuration, the stresses, and the deflections or displacements, and these have to be in appropriate axes. So I hope you can now progress with your virtual engineering analysis, and hopefully through the FEA analysis you can verify the various examples and exercises posed in this presentation. And for interest, considering the problem of example 3 or exercise 3, here was a finite element model constructed to solve those problems. It's fully fixed at this end, left hand end, in all 6 degrees of freedom, so there's the restraints on the left hand end, and at the right hand free end the loads were applied. Load P, load W, lateral load F. And then once the section and material properties are included, the finite element model can be analysed using a linear static analysis from which we can output stresses and deflections. These can then be compared to our hand calculations to see the correlation between classical theory and a computer-based finite element analysis. And here's the bibliography used to help generate the presentation, and I hope this has been of interest to you and will help you progress in your virtual analysis work. Thank you for viewing.